All right, welcome, ladies and gentlemen, to section 8.2, the beginning of our studies of ellipses. So last study was on the parabola. Now our second conic section being the ellipse. So what we're going to be looking at is obviously the equations for ellipses, a new term called eccentricity, and another reflective property of ellipses. This is another kind of cool reflective property. Let's just go ahead and get into it here. Our definition, you may know a little bit already what an ellipse is. It's basically this shape. Some of you would say that's an oval. It's not really. It's an ellipse. And ellipse, by definition, is a set of all points whose distances from two fixed points called the foci have a constant sum. So in an ellipse, you have a few different things. You have foci number one, or focus number one. You have the center, and you have focus number two. So there's two foci or foci. I don't care how you pronounce it. I've always pronounced it foci, but the other one is correct. And what this is the distance from F1 to some point on the line, and that. So that point right there, let's call that M. If I was to say that F1 to M was 6 and this was 5, the sum of those two distances is 11. And so the set of all points whose distances from two set points have a constant sum. So if I was to find any other distance here, and to this point and this point, let's say this was an 8 and a 3, and what you'd notice is the sum is still the same. So 8 and 3 make 11, and the sum would remain the same. All right, so that's the definition of an ellipse. It's our definition of an ellipse. And what we now want to do is we want to look at the equation and some the way things kind of interact with one another on this ellipse. So I didn't do this as a list of things. I just did this as a straight, here you go. All right, so what you'll notice here is the equation kind of looks like a circle where we've got x minus h squared plus y minus k squared, and then you've got something over a squared and something over b squared. A and b come from the ellipse themselves. What you will note is that h comma k is your center, right? Because your ellipse with center hk. And what we're going to be noticing here is obviously down here in this Pythagorean relation, I'll explain this a little bit more, but this is obviously the longest length. Using Pythagorean, whatever we say is equal to the sum of two squares is the longest side. So we kind of call this the hypotenuse, right? Well, if A is the longest side, and you notice that A goes underneath the X, this particular ellipse is going to be short and fat, is what I call it. And I have my two focal points, and I have my center. All right, so this is a short and fat ellipse. The distance from center to focal point is the value c. And the distance from center, and by the way, vertices, I forgot to put that on here. Vertices are right here. So this is vertex 1, this is vertex 2. The distance from vertex to center is A. So this is very key that you understand this, that the distance from the center to the vertex is A, and the distance from center to focus is C. And then down here, you'll notice that that means semi-major. This is the semi-major axis from from vertex to center. The major axis is all the way through, or the focal axis. Goes all the way through all of these points. And the length of that from V1 to V2 is obviously 2a. And then there's different relationships you can notice. Notice that the focal point to vertex is the distance a minus c. That's something that's going to come up a little bit later. What you'll notice is this distance. This is not a vertex, by the way. This is not a vertex. This is just a point out here. This distance is b. All right, so b is not too often used unless we really want to graph this, which we're not going to do a whole lot of, but if we really wanted to graph it, we could use the value of b and then sketch this arc here. All right, so pay attention here. The focal axis is y equals k. The foci, because this is short and fat, the foci is going to be c units to the left and to the right of my center. The semi-major axis length is a. The semi-minor axis length is b. And please make very big note of this. Too many people get this wrong because they think it's a squared plus b squared equals c squared, where it's not. Okay, so a is the longest length in an ellipse. And what you might guess is what comes next is this is the short fat version, so we have the tall skinny version. Now I did click a button, so pay attention here. Notice on this version, the one we just did, that the largest value, the a value, goes underneath the x squared. Whereas with the other value, when a squared is biggest and it goes underneath the y value, then we know that this is a tall, skinny ellipse. So we have our points in here. We have focal point 1, my center, focal point 2, vertex 2, and vertex 1. And you'll notice that my center is still HK. In this case, the A is biggest. Notice the Pythagorean relation is still the same. A squared equals B squared plus C squared. The major axis length, all right, so distance from vertex to center is A. The distance from focus to center is C. And the distance from this side to C, or to the center, is B. All right, and you'll notice here for the foci and the vertices, because this is a tall skinny, it's going to move up and down from my center point. All right, so what you need to big note here is this first statement on both of these last two pages. This is what we're going to call standard form for an ellipse. So if it asks you to write the problem in standard form, this is how you need to write it. Notice that both of them were equal to 1, and that's the key. It has to equal 1. All right, so let's take a look at a few examples here. First example, I want to find the equation of an ellipse with major axis endpoints and a minor axis length of 4. And when this is talking about minor axis length, that means the entire length. So again, the same thing I did with parabolas is I like to just graph it. At -2, -1, I have a vertex, right? Because it's major axis endpoints. And at 8, 1, -1, I have another vertex. Well, in order to write an equation, first of all, because these are vertices, this is my major axis, I know this is short and fat. So I know it automatically has to be x minus h squared over a squared plus y minus k squared over b squared equals 1. Now the key is just to figure out what's a, what's b, what's h, and what's k. Now, the center has to be halfway between my two vertices. Well, halfway between. The distance from here to here is 10, so halfway between is 5. If I go 5 units in either direction, this comes out to a 3. So my center is at the point 3, -1. So I can start writing some stuff in here. I can say I have the equation x minus 3 from my vertex, or sorry, from my center, over something, plus y minus k. K is -1, so it's actually a +1, over, and equals 1. We got to figure out what it's over. Now, because the center is halfway between the two vertices, the distance from center to vertex is a. Well, that means a is 5 because that's the distance from center to vertex, and that's what we figured out a minute ago. So if a is 5, that means a squared is 25. Oops. And we actually already know b as well. The minor axis length is this direction, and we said that this direction is 4, which means b is 2. So this tells me that b equals 4, or sorry, 2b equals 4, therefore b is 2. And if I square that, I get 4, and there we have an answer. All right, so it's just about picking out A, B, H, and K. Now, this one gave me A and B pretty quickly, but not always the case. Oops, let me get erased to that. What if I wanted to find the vertices and the foci of this ellipse? Well, I would need to put it in standard form. So I need to divide by 36. So I have x squared, that's not negative x squared, x squared over 9 plus y squared over 4 equals 1. Now, because 9 is bigger than 4, that means it's a short fat with a center at 0, 0. So I know my center is at 0, 0. And when I look at this, I know that a squared equals 9, and therefore a is 3. I know b squared is 4, which means b is 2, which doesn't really actually help me with anything. But I do need to figure out what c is because that has to do with the foci. So I would say a squared equals b squared plus c squared, using my Pythagorean relation. And I would say 9 equals 4 plus c squared. C squared equals 5. So therefore c is root 5. So I need to know what c is root 5. And then I just need to use these pieces of information. To go from center to vertex is a units away. And because it's going left and right, I'm going to change the x values. So my vertices are 3 units to the right of 0 and 3 units to the left of 0. And my foci are root 5 to the right of 0 and root 5 to the left of 0. And there we go. There's our foci and vertices. And I will allow you to write plus and minus 3, 0 and plus and minus root 5, 0. But don't really get into the habit of doing this because it's just more, I like it better when you write all 4 out. Okay. So again, we found A, we found C, just in order to find the rest of the pieces being asked for. What if I wanted to find the center, vertices, and foci of this ellipse? So the center should be easy because it's automatically given to you. The center is -2, 5, because that's the piece up here. The x goes with the 2 and the y goes with the 5. And then I need to figure out, first of all, is it tall and skinny or short and fat? Well, this, I shouldn't have done that. 9 is the smaller number, which means 9 is actually the B, and 49 is the A. A is actually 7, and B is 3. right? Because 49 is a squared. Which means, because the bigger number is under the y, that it's a tall skinny. It's kind of slanted, apparently. So we go along doing this. If my center is at negative 2, 5, and it's tall and skinny, I'm going to change my y values to get my vertices. So my vertices should be easy. My negative 2 stays the same, and my negative 2 stays the same. And I'm going to go up 7 units, and I'm going to go down 7 units from 5. But I can't find my foci until I have found my c value. However, we do know that the foci are both at negative 2 because the x value doesn't change. So I have 49 equals 9 plus c squared. So c squared is 40. So c is equal to 2 square roots of 10. And here's where you got to write out a little bit of math. Don't bother with the decimals here, but it is 5 plus 2 root 10 and 5 minus 2 root 10 because we're going up and down from the 5. All right. So far, so good. You're getting it all. I know you are. You guys are smart kids. Let's try this. We want to prove that this quadratic looking thing is an equation of an ellipse. And again, this is where completing the square is going to come in handy for you. So what we want to do is we want to get all the x's together and all the y's together and all the constants on the opposite side. So hopefully I have enough room here. I'm going to do this right up here first. So I'm going to say I have 3x squared minus 12x plus blank, because I need to complete the square. Actually, I'm not even going to write that yet because that's not what I want. I have a plus 5y squared plus 30y equals negative 42. Now, you might recall, in order to complete the square, you need to factor out the number in front of the quadratic. So I'm going to factor out the 3, and I get x squared minus 4x. Now I can do the plus blank. Plus 5 times y squared plus 6y plus blank equals negative 42 plus blank plus blank. And now I need to cut 4 in half and square it, which gets me a 4. I need to cut 6 in half and square it, which gets me a 9. Now you have to be careful when you plug the numbers in over here because it's not a 9 and a 4. This 4 is connected to this 3, so it's really 3 times 4, so I have to add a 12. This is really 5 times 9, so I have to add a 45. Then I can do a little factoring. Simplify this. Negative 42 plus 45 is 3, plus 12 is 15. And then because standard form has a 1 here, we need to divide both sides by 15. And if I divide both sides by 15, I get x minus 2 squared over 5 plus y plus 3 squared over 3 equals 1. And that is for sure an equation of an ellipse. It even has a vertex, a center of 2, negative 3. It's a short and fat because the 5 is bigger than 3. They're not nice numbers, so you're not going to get nice vertices or foci. All right, but you notice that completing the square comes in handy. We did this a little bit already. I remember I refreshed your memory on that. Okay, if you wanted to graph on a calculator, you actually have to solve for y, which is not very fun. But I would suggest Desmos because you can actually type this into Desmos. Make sure you actually do put equals to 1. And you can actually see some things on that ellipse. I don't remember exactly how much they actually show you, but Desmos is pretty handy when you're trying to graph ellipses on a calculator. All right, so as I promised, I teach you a new word today, eccentricity. Eccentricity is defined as the letter E, as being C over A. And the square root just comes from the fact that A squared equals B squared plus C squared. So if I wanted to get C by itself, I would say C squared equals A squared minus B squared, and therefore C is the square root of A squared minus B squared, right? Pretty simple, straightforward, that's where it comes from. And what eccentricity basically does is it tells you the shape of the ellipse. It tells you if it's really skinny or really fat, or if it's closer to a circle or whatnot. E is defined between 0 and 1 for us. And at E equals to 0, that's basically telling me that C is 0. So the distance from center to focus is 0, which actually means that it's a circle. And this is when A equals B also. So when A is the same, so the distance from center to vertex is the same thing as the distance from center to side. That should tell me that that is equal to a circle. We call it degenerates because it goes from an ellipse and gets smaller into a circle. As E gets closer to 1, C is becoming the same length as 1, and things get really weird, and we actually get our hyperbolas. Okay, so it gets, as you get B getting closer to 0, the ellipse gets super, super skinny or super elongated. What I do want to picture is something in science, in astronomy really, when you are dealing with the elliptical orbits of a planet. Here's what's interesting. If this is Earth's orbit, some people think that haven't studied this, they think that the sun is the center of our orbit. It's not. The center of our orbit is just some spot in space. The sun is actually a focal point. Sun is actually a focal point of our elliptical orbit. And what comes up is the perihelion and the aphelion. The aphelion is the longest distance we are from the sun. And this is, let's use a different color. So let's say the Earth is here. Then this is the aphelion, or aphelion. Helio meaning sun, by the way. Helio. And aphelion is the distance, since this is the center. Center to vertex is A. Center to focus is C. That means this is the distance of A plus C. And then in a different color here, we can say, let's say we were at the closest point to the sun. That is our perihelion. Perihelion. And that distance is, the distance from center to vertex is A. This distance is C, so it's actually A minus C. And that comes in handy in a couple word problems, so hopefully you're paying attention here. And last but not least, we're going to look at the reflective properties. So this is kind of a cool property. If you were to have an ellipse and you rotated it around the axis of symmetry, you would have an ellipsoid. And we actually do use this for light and sound. If you've ever been under the spotlight in a play or a musical or anything like that, or on stage at all, a spotlight actually normally uses an ellipsoid light, not a parabolic light. And some of these other things, whispering galleries, I'll talk about those hopefully in class at some point in time if I remember. The lithotripter, whatever it is actually in your textbook. They talk about it a little bit, how to get rid of kidney stones. But what it is all waves emitting from a focal point will reflect directly to the other focal point. So if you had some sort of an elliptical shape, and you had a focal point here, and a focal point here, and you sent out some sort of waves from this focal point, and it came up here and it hit that side, that would automatically reflect to the other focal point. But if you're standing anywhere else and you go up here, it doesn't bounce directly to anything else. So if you're going from one focal point to the other focal point, you can just send those waves back and forth. And we use these in lots of stuff. But the coolest one is the whispering gallery. Is actually if your building is set up as an ellipse or an ellipsoid of some sort, if you are standing in one spot, if you're standing on the focal point, you can whisper and the sound will actually reflect off of the correct walls and it will bounce over to the person standing at the other focal point. So you can basically whisper and be heard by the other person all the way across a room, which I think is kind of cool. And it would be something worth visiting if you ever had the chance. There's not very many of them. I know of one in Washington, D.C. somewhere, and there's not very many other ones around. They're kind of cool. They take some work to actually do, obviously. All right, so those are the cool things there for that. Here is your assignment. Hope you guys learned a couple things today. I will see you guys tomorrow.